review and extend what I did. So part of this is to maybe explain it more carefully and also indicate how you bring pseudo-differential operators into the picture, because it's a modification of it. So let me remind you, the setting, we have a compact manifold, smooth, a differential operator, on this manifold. In interesting cases, there will be vector bundles around, but it just makes everything even more cumbersome. So I'm just going to assume it's scalar. Okay, from this data, I produced what I call the fat P. Okay, this is also a differential operator. But on the tangent groupoid. And just briefly, it doesn't really matter, it's just introductions, but so at t equals 0, the phi of the tangent groupoid is the tangent space. So then we have what I will, it's not the symbol because it's the Fourier dual of the symbol. It's operators. Okay, the Fourier transform is the symbol. So some people call it the co-symbol. I kind of like that word. But essentially, it's the symbol or the principal symbol. And t, all other values of t, it's essentially the operator itself, except you have to rescale it by a constant. Again, appropriately interpreted, etc., which I explained yesterday. So in a very sort of rough way, what you can say is what we've achieved is that the symbol of the operator and the operator are glued together in a smooth way. Right? It's not just two separate things that are related. They're actually smoothly connected into a single object. Again? Yeah, well, later. Yes. I'll repeat it because I think it's worth repeating. But yeah, I agree. But I'm just telling you what I'm going to do today. So yes, I will repeat the picture. Yeah, absolutely. So if P is elliptic, if you don't know what that is, it's a little too bad, but it's roughly this. It means that its symbol is invertible. So symbol, remember, was the dual of this thing, so that's a function on the cotangent space. Right, so it's a polynomial in C, so it's invertible, non-zero if you like, except if C is 0. Think of the Laplacian, that's the archetypal elliptic operator, or Dirac operator. Okay, so that's the definition, and then P itself is invertible, but modulo smoothing operators, which I will follow your convention of minus infinity here. So this is, if you like, the algebra, a convolution algebra of smooth functions, but okay, more or less. Okay, so so both are almost invertible, not quite, up to something. And okay, so what this means for the fat P, if you look at it carefully, is that this is invertible. Well, invertible, okay, so invertible, what does invertible mean? This is a function, so I know what invertible means. It has another function that's its inverse. Here, invertible, well, it's a differential operator, but the inverse is obviously not a differential operator. So it's invertible in something else. So this is pseudo-different, the inverse, quasi-inverse is a pseudo-differential operator. And here, invertible in some other sense that I have to specify. Okay, the inverse is something. But so this is invertible in a new algebra that I'm introducing here. So the algebra of certain types of distributions on the groupoid. Modulo the smooth ones. and I was a little quick, I think, on this point, so I want to explain that more carefully. And what does this buy you? Okay, now you can just treat this as a ring, and this is a two-sided ideal, and then by a general construction, which I'll also repeat in K-theory, you get a K-theory element in the K-theory of this ideal. Of course, this is algebraic initially. Then you close it up to get the C-star algebra, so you get a map in algebraic K-theory. But for C-star algebra, algebraic K-theory is topological K-theory, so this is just the usual. And okay, and then the fact that you have a single K-theory element here allows you to define an index map. So here you evaluate at 0. So you get what? The C-star algebra of the 0, 5, which is Tm. Okay, so that's C0 of T star M on the Fourier transform. So it's just topological K-theory of T star M. And of course, the element you get is what normally is the element associated to the symbol. And this is an isomorphism because the kernel is contractible. The kernel of the evaluation map is contractible, so these are isomorphic K-theories. And then you can evaluate at 1. You get the K-theory of the compact operators, which is Z. So the index, this is the index of P, interpreted as a difference of projections. Okay, so the projection onto the kernel and projection on the kernel of P star, if you like. Formal difference of two projections. And so there's a map here, which is just the inverse of this map, composed with this evaluation at 1. And then we have a theorem, okay, that says that, so there's a map from the K-theory of T star M to Z, which was originally defined by T and Singer, called the analytic index, and this says that, right, so it maps the symbol of an elliptic operator to the index of the elliptic operator. But the point of this whole construction here is to show that, okay, this map is induced by the tangent groupoid. Okay, so then you have a handle on it, and you can try to somehow derive what the formula is topologically. Now, all of this, the fact that this is the case is a one-line comment in Con that simply says that it is the case. Okay, so, all right. So what I want to do today is go over this in more detail. In particular, explain this algebra. So this is a new algebra I'm introducing. So I want to explain a little more carefully what it is, and then how this construction works. And then hopefully tomorrow, I'll show you that once this is okay. Once you understand this in sort of the cleanest possible way, then it's not so hard to adapt it to more complicated settings, because you basically repeat everything, like literally, without almost no modifications. The only issue will be to define an appropriate tangent groupoid in a different setting, and once you have it, you just repeat all the steps verbatim. Okay, that's. So the way I present this is pretty much the way that generalizes. Okay, so you can do it in other ways probably. Which condition at the bottom? You can make it a definition if you like, yeah.
No, I mean, is that from that condition that, because if P is elliptic, then that P is also elliptic, yes?
Well, no, because okay. So first of all, it only differentiates in the source fiber direction, so it's already not elliptic, right? Elliptic means, well, morally speaking, it differentiates equally in all directions, so it's certainly not elliptic in the ordinary sense as an operator. All right, so let's try to clarify some of these things. So I have to review a little bit of operator kernel stuff. So let's start with something very lowbrow. So given a measure or density lambda on M and a function, let's say smooth one, then you get an operator, right, the usual one. So TF at x, integral f x y. Okay. Right, the usual way you get an operator out of a kernel. Now, more generally, now you need actual theory. If you have a linear operator, continuous operator from C to infinity of M to distributions, so any operator you will ever encounter is probably this type, because smooth functions with complex support are as nice as it gets, and distributions are as terrible as it gets. So, right, you have the smallest possible domain and the largest possible range. So probably anything you could care about is of this type. This has to be continuous for the appropriate topologies, linear. Okay, and then there's this beautiful theory of operator kernels that says that this is basically given by an operator kernel which lives in what you would think from linear algebra. So you take this guy, which is the target, tensor with the dual of the domain, so that's tensor with, again, distributions. And if you take the course on complicated tensor products, then you know that this is this thing. Okay? So everything you would hope actually works, but it's a non-trivial amount of work to show this. Okay. But so, okay, what's the lesson here? That a Schwarz kernel really is a distribution on M plus M, not just a function. And the other thing I want to emphasize that in this case, there's no measure. Okay, so this lambda is somehow absorbed in K itself. Then you don't need this measure, okay, to define the operator. All right, so now I want to plug a slightly different point of view. Well, K lives where? Oh, okay, sorry, yes. K, yeah, sorry, thank you. Yes. Yeah, thank you. All right, so a differential operator, or later a pseudo-differential operator. Well, it's not quite this bad, right? It maps smooth functions to smooth functions, so. And whatever type of pseudo-differential operator you might invent, it certainly maps smooth functions to smooth functions. Any reasonable calculus of any bizarre type will do this. Otherwise, it's not properly called pseudo-differential. Okay. So, all right. So we'll play the same game. This means that our operator kernel, okay, so the range is now C infinity of M, tensor with the dual of this thing, so that's compactly supported distributions. And with a little bit of faith, this is smooth functions from M into compactly supported distributions. Okay. Now, these things actually form an algebra, unlike these things. Okay, this is already clear. I mean, you're mapping complex support smooth functions into some mess, and then you can, if you have another one of these, it doesn't work. Okay, but of course these can be composed because they have the same domain and range, and this can be seen in this guy. Right? If you have two of these kernels, so formally you get right, you have C infinity tensored with compactly supported distributions, tensor with C infinity tensored compactly supported distributions. And you just contract in the middle as usual, the way you compose matrices, and you get a composition. Right? For pseudo-differential they are. But I'm just, for now, large class, yeah. So, Right, so whereas normally you would say, okay, so this is naive, this is sort of sophisticated, and I'm just modifying it slightly. It's not, I don't think of Schwartz kernels here as distributions on M cross M. I think of them as smooth families of distributions, one in each fiber. Okay, and then it's an actual algebra. You can compose such things. Okay, so that's the picture. So here, well, let me not write that down. So I want to generalize this from M cross M to Lie groupoids G. Right, that's the goal. So this, you can think of this as the motivating example, or one of the two motivating examples. The other motivating example being the t equals 0 fiber, Tm. Okay, what do you want on Tm? You want, okay, some operator in each fiber given by convolution by distribution, and you want some smooth family of such things. Okay, so it's a similar kind of thing. So that these two examples motivate trying to do this on groupoids, in general, Lie groupoids. And so that's what this algebra is going to be. Okay, now I'm going to be very patient. Where you can think of if there are any questions they should ask. All right, so this is a motivating example for the following construction. G is a Lie groupoid. Right, so generalizing, as I said, M cross M. And, okay, I haven't made up my mind about right invariance versus left invariance and which one is better or more convenient. So, unfortunately, since I gave this example, I have to switch to left invariant to make everything okay. But you have to forgive me, I couldn't get it all to work out. So I'm putting an R here instead of an S, which is the range instead of the source. So what is this? These are smooth families of distributions U sub x in what? In, okay, I think it's an upper X, which is the inverse, the range fiber of X for any point in the unit space. Okay? So that's exactly what I have up there, because the, all right, those are smooth functions, so the M on the left is the range. That's why I need, and the distribution is on the range fiber, which is the M, copy of M on the right. So this generalizes that thing up there. All right, so what is a smooth family? Well, okay, so if f, well, phi is a test function on the groupoid, an entire groupoid, let's say phi sub x is the restriction of phi to this fiber, then you have a function and that should be a smooth function. But on the base. So another way to define these things, which I find a little bit less concrete or intuitive, is that U is actually a continuous map from C infinity G to C infinity G naught, which is continuous. But it's also a C infinity G naught module map. Where this is a C infinity G naught module by pulling back with the range map. Okay, so whichever point of view you like, you can show that they're equivalent. Okay. Well, once you've defined C infinity family. So you can take this as the definition if you like. All right, so those are the objects in a set. Okay, the sort of families of distributions. And now, so as I said, motivated by that example and TM and wanting to do something on the tangent groupoid, you sort of have the hope that this is maybe an algebra in general, which would be nice because you don't need Haar systems or half densities or anything of the type. And this algebra will absorb all possible pseudo-differential operators as a sub-algebra. So that would be nice. Okay, so I've been thinking about how do you do convolution, and it took me a while, and then it's kind of embarrassing that the answer is extremely simple. So convolution of two elements in this set is defined as follows. So again, for a test function on the group G, on the groupoid G, you define the convolution product evaluated on phi as follows. So I write the formula, but then the thing is to actually make sense of the formula, but it's not too hard. First thing to do if you see this is to just think of group and convince yourself that if you have a group that this really is convolution. Okay, this is how you define convolution of distributions on a group. And so it seems fairly reasonable to try to write the exact same thing. If it works, then it's correct. And it works. So the interpretation is as follows. First, you have to interpret this thing here as a function of gamma 1. So what is gamma? This is a function which sends gamma 1, which is an element in the groupoid, to what? Okay, so this here is a function of two variables, so you have to think of it as a function. Since this is a distribution depending on gamma 2, so this should be a function depending on gamma 2, so let's call this 5 gamma 1. Right, so it's a translate of phi, if you like. And what do you evaluate on that? Well, V, but which V? So V on the range fiber of gamma 1. So, sorry, I'm confused again. The source of gamma 1. So we have this picture here, gamma 1, gamma 2. Right, they're composable arrows. That's implied in this formula that gamma 1, gamma 2 are composable arrows. So the source of gamma 1 is the range of gamma 2. Okay, so gamma 2 actually varies over the range fiber of the source of gamma 1. Okay, so this is a well-defined pairing, which gives a number, so this gives a function. And you call that psi, and then so this is just U evaluated on psi. And then if you actually look in the book on how you convolve distributions, it's actually defined in this way as well sometimes. They're not G invariant. They're not G invariant. Mm-hmm. Yeah, I'm mostly motivated by actual problems and trying to solve things. So this is motivated by the fact that it works. But yeah, it would be nice if it fit into some conceptual picture. All right, so is this clear? This is convolution. So, And what I like about it is that it's just like literally the same, exact same formulas for groups. There's you know, once you interpret it correctly. And this is the interpretation. So, what goes wrong initially when I try to understand is that, you know, if you think of v in this terms, you would get a function on the base, and then there's nothing you can do with u. So that was, you know, so the only real thing is to interpret this as a function of on the groupoid g. But then with that slight modification, it all makes sense. All right, so we have a new algebra. And so what I want to plug that algebra a little bit and convince you that it's an extremely useful algebra in index theory. And it's more convenient than the half-density thing that is more usually taken as the canonical, like Hausdorff system-free algebra. All right, so let me just not stray too far from the familiar, show you how this relates to the usual convolution product, which does use a Hausdorff system. Okay, just it's not particularly deep, but it helps maybe to solidify the notion. So to get the usual convolution, what you do is what I also indicated for groups. So you have compactly supported smooth functions of G. Well, they're not distributions, they're functions, but let's not be deterred. There's an obvious inclusion map here, where you take a function and you map it to a function times a Hausdorff system. Now, okay, now my Hausdorff system needs to be left invariant. So lambda, which is a family of measures or densities, right, so what we have is, now we have range maps. So you have these measures here in each fiber. So if I multiply this with a function, then you get, and the function is compactly supported, then you get a family of compactly supported distributions. Okay? So that's how you get from functions using a Hausdorff system to distributions. This is another motivation for using this definition, because the Haar measure is basically more or less an object of that type, except for the fact that it's not compactly supported. Okay. So this is how functions go to, I'll call them fiber distributions or something. All right, so then we do a little check. So if u is f times lambda, b is g times lambda for two functions on the groupoid, then u convolve with v evaluated on phi. It becomes very explicit. This is f of gamma 1, d lambda gamma 1. That's u of gamma 1. Integral g of gamma 2, d lambda gamma 2, and then phi of gamma 1, gamma 2. And now you have to make sense of this. So you do, as usual, you have to do some coordinate transformation. This is where the invariance of the Hausdorff system comes in. So you replace gamma 2 with gamma 1 inverse gamma 2. So in this case, I have to multiply on the left. So my Hausdorff system has to be left invariant. And then you get f gamma 1, g gamma 1 inverse gamma 2, d lambda gamma 1. And then if you like, you put this whole thing in parentheses and get another integral phi gamma 2, d lambda gamma 2. And so this is the same, of course, as the usual f convolved with g times lambda evaluated on phi. Okay, so it's just, like I said, it's not particularly deep. I just want to reinforce that this definition really extends the usual one. And okay, so like I said, but I think one of the virtues is that this thing includes, so this is a remark, any algebra of pseudo-differential operators, let's say the classical ones, on a groupoid sits inside this algebra. Right, so it's much too big, but it doesn't matter. It's an algebra. Okay, so that's part one thing I wanted to clarify. All right, go again. This cannot be done in less than 4 turns, right? So back to operators on manifolds. So we're going to now have P be a pseudo-differential operator on M. Again, compact for simplicity. So as we saw it, Schwarz kernel can be thought of as an element in here. Well, okay. This is what I now call the distribution algebra of the pair groupoid. All right, so what am I going to do? So now I'll draw the picture that Masoud asked for. So let me remind you of the tangent groupoid picture, or a tangent groupoid picture. Here's M. So you think of okay, this one line represents M. This is the parameter space, so R, or restricted to 0, 1 if you like that better. And then at t equals 0, we have the tangent bundle. So there are fibers here, which are tangent spaces. So I need the range map in this case instead of the source map. Okay, but still the same thing. And then, so here the base, that's the unit space. Oh, sorry about that. M cross R is this space of units or objects, right? 1 M for every t. And then at other values of t, t is not 0. We have M cross M, so the range fibers are copies of M. And these points here are the points on the diagonal. So this is M comma M. Yeah. Yeah. So if you take M equals R, you get the Heisenberg group. Well, the C. The C-star algebra of the tangent groupoid for R is the C-star algebra of the Heisenberg group. Yeah. Right, which again indicates it's closely related to quantization. Yeah. All right, so that's the picture. And yeah, so what okay, what's not in the picture, what we should sort of imagine is that as we move these fibers of M closer to t equals 0, they're stretched out. So you're zoning in on a very small neighborhood of M cross M as you get closer to these tangent fibers, which obviously is intuitively correct. A tangent vector is an infinitesimal displacement. So All right, so that's the picture. So now we have a pseudo-differential operator. So, okay, why is this, this thing is sort of, okay, partly also just motivated by this groupoid, this particular one. What we have here for a pseudo-differential operator, say at t is not 0, you exactly get distributions in these vertical fibers. And as Masoud indicated, they're actually more special for a pseudo-differential operator. It's not just some random family. All the singularities, all the distributional singularities are actually on the diagonal, which means they're here on the unit space of the groupoid. And the distribution away from the unit element is just a smooth function. Okay, so it's almost a smooth function, except on the unit space you get it has a distributional singularity. Okay. So it lives here, and now what I'm going to do, so you put, well, whatever that means. So put k at t equals 1. Okay, and then you just do exactly what I said last time. So you do t to the dk at t is not 0, where d is the order of p, which in this case is any old integer. Could be negative as well. Okay, so just steal this from the example of differential operators. So what are we going to, so now you could, okay, in principle, this determines what you should put at t equals 0, because I want a smooth thing. Okay, I have put distributions on all fibers here except at t equals 0, and I want a smooth family. So if there exists a possible way of doing this, there's only one. So now you need to know a little bit of pseudo-differential operators to understand what's going on. So most people do pseudo-differential operators in the Fourier picture. But in this framework, it's much more convenient to just stay with the old-fashioned approaches. You just work with the kernels, so don't take any Fourier transforms. What happens? So you have these distributions here with singularities here. You move them closer and closer to 0, and in some sense, you're just rescaling. You're stretching them out. But you're compensating by then also kind of pushing them down if they have, say, if they have positive order. So what that means is that, so what is a pseudo-differential operator in this picture? It's just, as Masoud indicates, like, so it's smooth outside of the diagonal, so the singularities are here. And a pseudo-differential calculus is just a way of controlling how horrible that singularity is. And what you impose is that the kernel sort of transversally, so exactly in the direction of these fibers, has an asymptotic expansion in homogeneous terms, exactly like a differential operator. Okay. So you have to make sense of asymptotic expansion. It's just modulo smooth functions.
So in this case, we will get that log singularity.
So the log singularity, I'm avoiding, but you can deal with that one too. So you have to modify it a little bit. So modulo smoothing, everything's modulo smoothing operators. Yeah, you're right. But the nice thing about the log term is that modulo smooth, it's actually in order, it's homogeneous of order 0. So that's the appropriate way of thinking. Yeah. But anyway, I didn't want to get into that. Yeah. Anyway, so what happens? You push this thing closer to 0. It stretches out. You multiply with t to the d, and just as for a differential operator, all the lower order terms in asymptotic expansion sort of vanish, and you're just left with the leading term in the asymptotic expansion, but now as a kernel, as a convolution operator, and it just becomes a convolution operator on this fiber. And that's the principal symbol, except it's the Fourier transform of the principal symbol. So co-symbol, if you like. It's a convolution operator, convolution by a distribution. Now, again, it's a little annoying because it's not a compactly supported distribution, because it's homogeneous. So it's, it can be compactly supported. Okay, so, well, then you do something brutal. You just sort of take a neighborhood. You just make it 0 outside of that neighborhood. Well, is that bad? No, it's just now I've modded out by smoothing operators, so it doesn't matter. It's totally irrelevant. So now everything's compactly supported, and you can convolve these things. Okay, so you're forced to do at 0. you get a family K sub m, say, of distributions with compact support on the tangent fiber, on the vector space. And this is the Fourier transform of the principal symbol at m. Modulo things of rapid decay. Okay, so, but it's a chopping thing, has a little bit of effect. But, okay. See, this is maybe a bad thing, it's a distribution, but the Fourier transform of something with compact support is analytic. So the Fourier transform is always a smooth function. Okay, so. But it's not going to be homogeneous because I chopped, so it's asymptotically homogeneous. Okay, so this is a slightly confusing picture if you're familiar with things, because what happens if I have a differential operator? I used to put P here, but now that's not exactly what I'm doing. I'm treating P, the Schwarz kernel of P. P is a local operator, so Schwarz kernel is actually supported on the diagonal. It's dead zero everywhere else. So you're like, what the hell is going on here? So at these points here, what you have is P evaluated on a delta function at that point, which is itself a distribution, and that's the distribution you put there. Okay, so that's how that fits in this picture. So it's slightly different than the picture I described last time. Okay, so now like I said, because my algebra is so huge, what I produce, let's call this fat P, just this entire whatever collection of things is in my convolution algebra, distribution convolution algebra of the tangent. That's how I got the fat P for arbitrary pseudo-differential operator. Okay. And because this construction is so generic that it will work in other calculi. The exact same thing happens. If you do the blow up appropriately, you're just going to pick up the leading term in the asymptotic expansion of the kernel of a pseudo-differential operator here, which will be its symbol in any reasonable calculus of any type. Okay, so this took me a while to figure out, because somehow I always thought, okay, a Schwarz kernel is a distribution, so I was looking for some way to convolve distributions on groupoids, and there's just no way you can do that. At least I couldn't figure out any way to do this. But I think this is the correct way. Okay. What I think I'll talk about next week, so this is another project, since this idea clarifies or simplifies a lot of the arguments in the index theorems quite a bit. Trying to go one step further is to actually define the pseudo-differential calculus. So to pick out which of these elements actually come from pseudo-differential operators by some intrinsic description. And then prove all the various properties of pseudo-differential calculi. So, but, you know, this definition is inherently coordinate invariant. I haven't used any coordinates in the definition of this thing. And so a lot of the problems in checking whether something is a well-defined calculus has to do with coordinate transformations. It's really tedious to check that everything, you know, that it's well-defined on a manifold, and this would take care of that. So that's kind of what we're working on right now. Yeah, so while I'm wasting time here, the calculus that I work in a lot is Heisenberg calculus, and Pierre Jules needs it for codimension 3 context structures. It's some generalized context structure. And he said, you know, is there such a calculus? I said, yeah, surely. But he's a very honest man, so he actually wants to see a reference, and then there is no reference. So then you find that there are various cases of that calculus where people have checked it, and they do it all slightly differently, and it's horrifically complicated in each case. So then I talked to one of these analysts, Charlie Epstein, he said, well, the only way to understand this calculus is to just do it yourself from scratch. And that's why everybody starts from, just does it himself in his own particular way. But it's not entirely clear if you look at these various approaches that it will work in all cases. Right? So that's another reason to try to really clarify this as much as possible, to just give a uniform way once and for all, so that you don't, for every single case, have to start from scratch. And you have sort of a nice way to check that these calculi actually exist. All right. Where am I? 4, 3, that's not it. 5. I haven't thought about that yet. Yeah, that's a good question. Yes, like I said, I have very limited purposes with this thing, so I haven't thought about that. Yeah. Yeah, that's a good question. So where I'm not even sure. So I haven't thought through what happens for non-compact manifolds, because you need proper supports. Yeah, proper supports implies certainly that these families are compactly supported in each fiber. But it's of course more than that. I have a feeling that this actually will work, but I have not checked it. I'm always a little nervous when you get to open manifolds. So there's some, if you're too glib, then there's some horror that happens at infinity that you didn't see coming. But I have a feeling I don't see any reason why it wouldn't work. Let me put it down. Yeah, exactly. Yeah. So yeah, it's worth trying and see if there's anything that goes wrong. So yeah, when I say M compact, I'm just it's just for safety purposes. It's not okay. So I can go back to so restate what I said at the beginning. So now the elliptic. Right, so in this picture, what that means is that, okay, because I've deviated ever so slightly from the symbol, or the co-symbol. I've chopped it and made it compactly supported. Okay, so that's another little detail, but it's worth considering. So let's say here we have Rn. This is Rn in one dimension. Okay, and then you have some kind of distribution, which is, say, maybe homogeneous of some degree or other with a singularity at the origin. So there's some derivative of the delta function here. Okay, but what I've done is I've chopped it. Okay, I made it compactly supported. So you throw away a little bit, but that little bit is smooth. Okay, so it's not so bad. So whereas the symbol is so that the Fourier dual will be invertible outside of 0. This thing in the convolution algebra, so this is case of X, case of M, I guess. In this algebra here, the definition of elliptic could be that this guy is invertible modulo CC infinity in the convolution sense. Right, so it's, again, so it's a slight, you have to just think a little bit. It's a technical detail, but so the invertibility of the symbol means that this, if you take the Fourier transform of this, then at infinity it's invertible. Okay, and that means exactly what it is equivalent. You can show it to this thing here. Okay. And so, so these are the kinds of things you have to think about. And so what we get in the end is that this fat P, this entire family, is invertible in this distribution algebra. But then modulo Okay, and now if M is not compact, you need to modify C sub C because it's not going to be compactly supported in M. Okay, but this is another here. So to just simplify, M is compact, so I can write this. And this is an ideal, two-sided. Okay, that was the. So everything, I think it takes care of a lot of technicalities. This is a very nice sort of algebraic statement. Okay. So that's what you get from an elliptic operator. And then, why this makes me happy is because I spent 9 months, in the Heisenberg calculus, but where everything's more complicated, and you don't know if it's true. This is the thing where reproving a T.S. Singer, you can be kind of sloppy because you know it's true. So you know if something looks like it's going to work, why bother with all the details? Because we already know the theorem is true anyway. You just want to conceptualize it, right? But if you try to actually prove something new, you have to be more careful. And so proving that. So we know that the symbol of an elliptic operator determines a K-theory class, as T.S. Singer explained, in the K-theory of the cotangent bundle. We also know that you can interpret the index of the operator P itself as a formal difference of two finite rank operators or projections, which is a K-theory class in the K-theory of the compact operators. Okay, so that's known. But now you want to somehow glue those K-theory classes together. So you have a specific one at T equals 0, which is topologically defined. And then you have the Fredholm index as a K-theory class for all other values of T. And you want to know that they somehow at least continuously glue together. But even better would be smoothly. Okay? And even checking that in the classical case is not entirely trivial, but checking it in a non-classical case like a Heisenberg calculus, that took a long time. It's just very, very painful. So if you suffered, then you can, but it's like if your shoes are like a size too small, it's really nice if you can take them off. And for most people, if you don't have shoes on, it might be inconvenient. But so it's hard to appreciate how happy this makes me because this gives me for free what I want. So now I'm just copying a little idea. Kahn's book, the red book, is full of many ideas. Okay. But one little one somewhere is this, that this gives you a K-theory class in the K-theory of this algebra. And this is how many, many index things arise. So make sure I'm not going over time. I have 1 minute. I started late. So, I won't write down the formula then. So, yeah, I should write down the formula, otherwise I'm just talking air. So, this is an idempotent. Okay, so I'm not going to check that for you. Q here is the inverse of P, fat Q. And then you have the usual S is the deviation from T. Is the other guy. Okay, this is an idempotent, and if you know that this is invertible modulo these guys, this is you can think of this as a smooth family of idempotents on the tangent groupoid. Comes for free. Okay, because this S and T, I've just proved that these are CC infinity. Okay, so that makes a lot of things a lot easier. So this means that if you take the K-theory class associated to the symbol, it will map to the index of the operator by the map induced by the tangent groupoid. Okay. Right. So this is the big reason for me for being happy about this. All right, I'll stop.
here again?